VisIt is a tool that's has really two focal points, and you can see them up here in the title. And so one of the focal points is on having a turnkey application. So something that people can download and use. It has documentations. You don't have to have me sitting next to you to be able to use it effectively. The other focal point is looking at the biggest data sets in the world. And so here we see one, a large data set. This actually isn't really large by today's standards, but at the time we'd never seen anything in the billions before when we looked at it back in 2006. And so the really big data sets that are being generated on the high-end supercomputers are really our target audience. So if you look at the bullets here, the bullets are saying these same things. Production end user tool, we have documentation, we have a users list, we know how you can download this product and start using it. And doing scientific visualization. Why what we do is called scientific visualization, other visualization is not called scientific visualization, I don't know. But scientific visualization means you're looking at three-dimensional things or two-dimensional things. Information visualization means there's no physical space associated with it. So if you're looking at, for example, this is a Rayleigh-Taylor instability. This is an example of a scientific visualization because it's something that happens in physical space. If you're looking at tax records, that's information visualization because it doesn't happen in physical space. And so we do some InfoVis techniques, but we're primarily geared around scientific visualization because we're supporting the simulations that are happening on the giant supercomputers. I should comment what this image is right here. This is, again, a Rayleigh-Taylor instability. And the idea is that you have a heavy fluid at the top and a light fluid at the bottom, and gravity is pulling the heavy fluid down into the light fluid. And so in this case, we loaded this large data set and we removed the pure heavy fluid at the top and the pure light fluid at the bottom, and we're looking at just the mixing regions of the two. And so as I already mentioned, this is a grid that's 3,000 points in height, in depth, and in width for a total of 27 billion mesh resolution points per time slice. In 2006, this was gigantic. Now we'll regularly see stuff that's on the order of several hundred billion. People are talking about having trillion-point meshes in the next few years. So this is a really exciting time to be in HPC, right? Things are getting bigger and bigger every day. And so to me, this is big data. I think the phrase big data is broader than just the usage that I'm saying there, but it's exciting to see these big data sets, data sets getting a factor of 10 bigger, every 4 or 5 years. So back to VisIt. VisIt is an open source code, and it's released under the BSD style license. So VisIt is like terribly named. It's terribly named because it's kind of cheesy. It's terribly named because if you Google it, you don't always find VisIt, although we're often #1, right? So Google is too smart for me, right? Because I've Googled it before, and so it always gives me the tool back. But I'd say about 80% of the time I give these tutorials, people double check and they type in VisIt, and we actually own the word VisIt. I don't know if that's the case today or not, but I'm sure someone will tell me whether we're #1 on Google. But the real reason it's a terrible name is because it limits the listener into thinking about a tool that does just visualization. And so we think about the tool being more than just a visualization tool. So we think about VisIt being about more than doing just visualization. And so I'm going to mention to you what these use cases are. And so the first one is clearly a visualization use case, and that's the notion of exploring your data, right? You've run a simulation, you don't know exactly what's going on inside the simulation, and you want to use visual techniques to understand what's inside your data set. And so this is the same data set using 3 different visualization techniques. And so one is just looking at the exterior of the data set and doing what's called pseudo coloring, which is something that Joe did a great setup where he was talking about these different techniques where we're mapping scalar values to colors. The one in the middle is an iso surface, so we're finding a surface of constant value and then coloring it by another field. And the one on the right is volume rendering, which Joe talked about again when he was talking about ray casting. And so this is clearly the sort of thing that you would expect a tool named VisIt to do. But we're also really interested in quantitative analysis, and I actually have a slide on the sort of quantitative analysis that we do. So let me just say that's a use case for us. Debugging, so I think it's kind of a dirty secret. Oh, I forgot I had another survey question. I'm sorry, let me jump out. Another survey question. How many of you consider yourselves to be computer scientists, and how many of you consider yourselves to be computational scientists? So let's start with computer scientists. Who's a computer scientist? Okay, good. And who's a computational scientist? Okay. What's that? Computational scientist. This is my problem man over here. So good. So I think the computational scientists, this will resonate with them, that in fact, often you use visualization to do debugging, right? You have a problem, you have a hot spot, you have your mesh tangled, and really you want to use a visualization tool to be able to show you where the problem occurred and hopefully why the problem occurred. And so we have a lot of functionality built in the tool to debug your data set, to say, at this location, these are the values, and we actually try to put it back into your notation, the terminology of your mesh, right? At this cell, at these points, these are the values, these are the neighboring cells, to give you all the information you need so you can actually figure out what went wrong. So we have a lot of cool debugging information there, and I'll show that off in the demo. Comparative analysis. So that's, of course, a cousin of quantitative analysis, but trying to figure out, does the simulation match the experiment? Are two simulations the same? How has the simulation changed over time? And then finally, presentation graphics. So making movies, images for PowerPoint, XY plots for your publication. So I think data exploration, presentation graphics, you would certainly expect that in a tool called VisIt. But these other use cases, I think, are really some of our bread and butter, and VisIt doesn't quite convey that. I had a program manager once say that we should rename it, and we should call it Paralysis for parallel analysis. But I thought that was the worst name ever. I don't want any product I'm associated with to be called Paralysis. So let's see, I'm not sure I need to go over these in so much depth because of Joe's good setup. Maybe I'll talk about them a little bit more when I show off VisIt. But at least I'll mention them really quick. I think that we have a great infrastructure for doing particle advection. Have you guys heard this word advection before? ADVECT. So it's a real word, although Microsoft Word doesn't think so, but it is. And it comes from the ocean modelers in terms of that if you have something, it's being displaced by the currents of the ocean is the most common usage of it. But the idea is that you can have massless particles, and you can displace or advect these particles and then do lots of interesting visualizations with them. And so the most standard visualization is these streamlines where you look at the path that the particle travels through. But it's actually, particle advection is kind of a foundational technique for flow visualization, and there's a lot of other techniques built on top of them, things like stream surfaces, finite time line above exponents, Poincare analysis. And so this is, I think, is a really neat way to look at flow visualizations, and we've invested a lot in this in terms of getting the parallelization and the efficiency right. Okay, so moving on to the next one, glyphing. So vector glyphs, tensor glyphs, Joe talked about that, and so he said that VisIt and ParaView are good at those, and we are. And so we have these sort of things. Pseudo-color rendering, so we already talked about this picture, and the idea that you can take scalar fields and map them to colors, and so blue is, in this case, low density, and red is high density. Volume rendering, and so this is a star exploding. There's a lot of stars exploding in supercomputing. So you see a lot of star explosion pictures. Molecular visualization, I agree with Joe's assessment that our tools actually, or at least I don't want to speak for Dave, he can tell you about whether he thinks ParaView is great at molecular visualization. We have a presence in this space, but I don't think that we would do as good as a VMD would. And then also, as I mentioned before, although we're primarily a SciViz tool, we have brought in some InfoViz techniques. And so here's an example of an InfoViz technique applied to scientific data, meaning data that's in physical space. And that's the example of parallel coordinates plots. And if we have time, I'll show one of those off. So like I said at the introduction slide, our tool has two focal points, and one is on having a product, and the other is being able to look at the biggest data sets in the world. And so how do we look at these really big data sets? The idea is, of course, we run in parallel, and if the data set is already divided into pieces, as you can see these each piece being its own color in the picture on the right, then we just partition these pieces over our parallel processing engine. And so if we want to look at this 27 billion cell data set, then we would take these 3,072 subgrids and divide them over however many processors we're running with. It could be 100 processors and they each get 30, or some would get 31, or it could be 1,000 processors and they each get 3, and some will get 4. And the idea is that there's this great property for a lot of visualization techniques. Many of them are embarrassingly parallel, that you can process your piece and not have to do any coordination with the other processing elements. And so that makes a lot of parallel visualization analysis pretty simple to do. Some of it's really hard to do. And so the pieces that are really hard to do are the pieces that we've really invested in. So VisIt is a vibrant project with a lot of participants. So the project started in 2000. And I guess, let's see, so just stepping outside my presentation for a second, I took a job at Livermore in 1999. I took a job because I wanted to get a PhD, and my wife said that she wanted to have a baby, I need to get a job and make money. And so I took this job where they said, oh, you can get a PhD, and on nights and weekends you can still work full time. And I said, oh, sounds great. And so that was not a smart decision. But what was smart about it was something that was really lucky that I didn't really plan on, which is I got into a place where really big things were happening. And so, Livermore was one of the leaders of HPC 5 years ago. Of course, now institutions like Argonne are leaders in HPC, and Livermore continues to be a leader. My home institution, Lawrence Berkeley, is a leader. But getting to a place where big things were happening was so fantastic for my career, to go and get onto a big project that created a lot of opportunities for me. And so I didn't have the recognition of that when I graduated, how important it was to get to a job like that. But for many of you that will be in that position, you consider what the opportunities are and how you're going to be able to grow and shine and be able to establish your career. And so for me, I just didn't think it through very well and got very lucky. But for all of you, hopefully you can make a more calculated decision. Okay, good. Stepping back into this presentation. So it started in 2000 because Livermore had a simulation program that's similar to SIDAC. So I guess, hopefully you're all familiar with SIDAC. It's the one that would be, that Argonne would be really involved with. And the one out of the Lawrence, Livermore, Los Alamos, Sandia side of the house is called ASC. And they were generating really big data sets, and they needed a parallel visualization tool to support those data sets. And so that's how the project started. In 2000, and it was actually a really successful project within Livermore, and then was really a powerful tool, and so it won an R&D 100 award, which is a big deal. And then the SIDAC program came along in 2006 and funded an institute called VisIt, which brought VisIt development out of Livermore and into a multi-institution space. So here we have listed Livermore, Berkeley, Oak Ridge, UC Davis, University of Utah, University of Texas is involved. My friend at the Swiss Supercomputing Center is really involved. Drives me nuts because I used to be like the guy that would come and give all the presentations, and then he swept up all the ones in Europe because he was local, and so he's the face of VisIt in Europe. So he gets all the really good assignments. And it's kept going, and so we had our 2.0 release a few years ago, and then the next round of SIDAC has been funded, and VisIt's still a piece of that. And it's quite a big project, so 75 person years of effort, 1.5 million lines of code. Okay. So here's an example of some analysis that we did inside VisIt. This is looking at turbulent flow, and so it was a large simulation, 4,000 cubed data being run at TAC, which is the Texas Advanced Computing Center down at the University of Texas, and so we were able to isolate what were called worms, areas of high entropy. And so, actually worms became a misnomer. They had several predecessor calculations where they would run at 256 cubed, 512 cubed, 1024 cubed, 2048 cubed, until they got up to this level. And so they had seen these features that would trace along like worms, and so they referred to them as worms. But as they got to a higher and higher resolution, as more and more supercomputing capability became available, they found that in fact the appearance stopped really being worm-like. And so we got involved with some interesting analysis where we wanted to be able to characterize the shapes of these and understand, what do the shapes look like, what were the average thicknesses, but also to understand the properties of these worms marrying, divorcing, being born, dying. And so, so that was a really interesting analysis effort. Part of it is that something that helped us do all the analysis is we had to identify connected components. And so the idea behind a connected component is, here's a worm. I call all this a worm because it's all touching. It's not touching this worm over here, so they're not connected, right? It's a very graph theoretical definition to call that a connected component. And so that's something that's an easy concept to describe, But it's a hard thing to calculate in a distributed memory parallel environment, right? I have a blob here, I have a blob here, maybe they're both on the same processor, and I see these blobs aren't connected. But over on this processor over here, there's a U that actually connects them up. And so you have to do, at a minimum, you have to do a lot of bookkeeping to be able to figure out that these two blobs are connected through a blob on the other processor. And then to make the problem even harder, you want to do it really efficiently, and so you have a lot of parallel coordination there. And so this is an example of the sort of research that we've gotten into VisIt to be able to really scale well, to perform efficiently in a distributed memory parallel environment. I promised a slide on analysis, and this one comes from Cyrus. This goes back to our Rayleigh-Taylor instability. And so the idea here was to be able to calculate the average density. Actually, I don't think he's looking at density here. I think he's looking at velocity. But the average velocity as a function of the height. And then once that average velocity is known, well, certainly you could plot it as a 1D curve. But he's actually put that velocity back onto the grid. And then he can difference it with the velocity from this data set and actually look at fluctuations that deviate from the average behavior for your height. And so it's really neat to be able to take this sort of analysis capability and fold it back into the visualizations you can do to create new derived fields that allow you to make novel visualizations. So let's see. So I've probably hammered home pretty well that VisIt's identity is on big data sets. And so here's some scaling studies we did. Gosh, I guess now these are 4 years old, but 4 years ago we wanted to look at how VisIt would perform on tomorrow's data sets. And so we started looking at trillions of cells using tens of thousands of cores. And we were really happy with the results. We found that VisIt itself scaled really well. I/O is a continuing problem. We heard Joe talk about co-processing and in situ. I think that's clearly going to be part of the future because I/O is our bottleneck now, and it's only going to get worse. But we went and showed that the rest of the techniques actually worked really well over a variety of computing platforms and using multiple visualization techniques. So let's see. So then the other half of what I've been trying to hit home is that we have a product. And so we have regular releases, about 6 releases a year, executables for Windows, Mac, Linux. There's actually an end-to-end script called Build VisIt, which downloads all the dependencies and builds the dependencies and then builds the software itself. In terms of customer support and training, we have a wiki. The wiki is pretty good, right? People put stuff up on the wiki. It's kind of really a staging area for stuff that becomes formal documentation. Email lists for users and developers. Like I said, we've offered about 25 tutorials. There's actually an 8-hour VisIt class that you can have offered at your institution that will make everyone go through the same exercises. And then various documentation on how to get your data into VisIt. That's often a crucial issue, and maybe something I can talk about at the end. Because if you can't read your data, you probably don't care about the Viz tool. How to use the Python interface, and then the general user's reference manual. So we support a lot of different mesh types. So curvilinear meshes, AMR meshes, unstructured meshes, of course regular meshes, as well as point meshes. And then we have notions of scalars and vectors and tensors. And for those that are running, let's see, Eulerian meshes or maybe adaptive Lagrangian Eulerian meshes, we support material volume fractions and do material interface reconstruction. That's actually something I'd say we're really, really good at. And also support species mass fractions for those that have a lot of mixing at the atomistic level. And so we support over 110 different file formats. So I didn't list them all here. I guess I want to preempt the question I get most often. We support HDF5, but I view HDF5 as an array writing library, and there are conventions on top of it. And so it's doubtful that we understand your conventions that you've placed on top of HDF5 unless we've already dealt with your data before. Now, as Joe mentioned in his talk, the way that people deal with this now is you can make an XML file that describes what those conventions are, and if you have that XML file, then VisIt has a reader for that, as I believe ParaView does as well. Okay, so I mentioned before that we have this parallel server, and but here's what the whole architecture looks like. The idea is it's client-server, and that you fire up a client on your desktop, and so you get all the interactivity in the user interface, and if the data set's small enough, you can do all the rendering locally on your desktop. And then on the server side, we're loading data in parallel, processing it in parallel, and then transferring the results from the server back to the client. And so we have a GUI, we have a Python interface, we have customizable Python clients. You can actually build your own streamlined interface. We've made that so that's, for me, it takes a couple hours. For a guy who's a real whiz at it, he can make you a custom interface in a half hour. It's actually pretty amazing how quickly they can put together interfaces now. And also we have a Java client. So good. So I mentioned I kind of gave this vague phrase about what gets sent back from the server to the client. The best case scenario is that you read some gigantic data set, you do some sort of reduction, because visualization often reduces what you're actually looking at, and the reduced data set is small enough that you can transfer it from the server to the client, right? You load in, billions of data points, you do an isosurface and generate millions of triangles, and then you send those millions of triangles over and you render it interactively there. That doesn't always work out. If you have a trillion cells, like I was talking about our trillion cell runs, if you do one of these data reductions, you might still have a billion triangles. It is definitely a bad plan to try to send a billion triangles over a network connection and then render it here locally on your client. So you have to have a backup plan. And in our case, the backup plan is that you do, the next slide shows it. In our case, the backup plan is that you leave the surface on each one of your MPI tasks. And each MPI task renders its piece. And then actually you can capture the depth information for where everything is in terms of how far away it is from the camera. And you can use that depth information to take these sub-images, and the phrase they use here is composite them together into a single image as if they'd all been rendered on a single machine, on a single MPI task. And so the idea then, going back a slide, is that it does this parallel rendering, and then it sends an image over the network. And then as the camera changes, it sends a new view frustum over to this parallel server, it generates a new image, and then sends the next image back. And it sounds really slow, but you can actually achieve about 10 frames a second through this sort of parallel rendering client-server design. And so that's, I think, pretty good. I actually don't know of any way to do that better. So let's see. VisIt is pretty extensible. So the majority of the code is written in C++. It's easy to write your own file format reader. I did this, I think kind of, to me, the predecessor of this venue is they used to have something called Snowbird, where it would be a lot of application scientists and then resource providers, and we get together for a week and we talk about our technologies and sling code together, and that's kind of how I view this summer school. And I gave a presentation at Snowbird once, and someone raised his hand and said he'd written his own file format reader in 2 hours, and that's awesome. So it's pretty easy to write custom file format readers for VisIt. Writing new plots and operators, which are concepts for how to render things and how to manipulate data. It's also possible, typically takes longer than 2 hours. You can provide new interfaces, Python, C++, and Java. In terms of the Python interface, we drive VisIt with Python, but actually you can put Python scripts into the server and have them execute in parallel on the server. And so we use Python at that level as well. And then I haven't really emphasized it in this presentation, but Joe's absolutely right about the need for in situ techniques. And in fact, we have a capability we call libsim, and you can take the VisIt server and actually compile it into your simulation code, and then the simulation code would effectively act as a server to VisIt's client. And so that's our current solution for in situ visualization. I've already mentioned there's a lot of research going on in VisIt, and so I'm not going to talk about any of these results. Going forward, we continue to look at parallel algorithms, and like everyone else, we're really interested in next generation architectures. Our next release should be hybrid parallel from the perspective that we have distributed memory parallelism, which we've always had, but now we'll use shared memory parallelism within a node, meaning multi-core CPU nodes. This doesn't sound like a great innovation. This is what you do if you wrote code today. But for the folks that were all getting started over a decade ago, it's actually some effort to bring in that type of flavor of parallelism. In terms of many-core parallelism, I think that's what we'll get in the next few years, but that's kind of an active area for us. Okay, so at the end of this, I'll show how to use VisIt on Tukey, which is the ALCF Viz machine. There's a little getting started page that ALCF put together, and so I think you guys all have access to my PDF on the website, and so here's a link to that page. And so there's actually an extra step here is you have to download this host profile, which typically we package with VisIt. We haven't got, the Tukey is new enough that we haven't gotten it packaged yet. And this host profile is, I think, something that VisIt does a good job of. in that it knows all the details about how to launch a job on a parallel machine, so it makes it transparent to you. And so it knows, for example, on the Argonne 2Q machine, if you want to run in parallel, you need to use the QSub and MPI run methods and how many processors and other little tricks to get the job through the submission queue. And so if you want to run VisIt on 2Key, that's how you do it. Yes, question back there? Nope. An arm stretching. Okay. Good. So I'm going to start doing a demonstration. Are there any questions about what I've talked about so far? Okay, good. And so if I double click right here on the pseudo-color plot, I bring up the attributes for how to control the pseudo-color plot. And the first thing I'm going to do is I'm going to say that I want these things to be much bigger so you can all see them. So now you can see this is just some small handful of points in space. And I don't want to use our point glyph, I want to use our sphere glyph. And so that makes them prettier. And there are other options. So maybe I don't want to use this color table. I want to use my personal favorite is the hot desaturated color table. But there are lots of different options. And so again, this is a toy data set. We've started with some random locations with values. And then since we have a lot of computational scientists in the room, if you have scattered data like this, there are various ways to interpolate that data onto a regular grid. And so this data set has two different interpolation methods in it, one called the Hardy global interpolation method and the other called the Shepherd global interpolation method. And so I'm going to switch now from looking at this point var to looking at the Hardy global method. And so now we're looking at this three-dimensional grid. And so I want to explore this data set for a few minutes and kind of try to see what's inside. So we started with this pseudo-color plot, and of course we don't know what's inside, and so we can now start adding various operators to it. So the first operator I'm going to add is the slice operator. And if I draw that, now we have a two-dimensional slice, and you can see my interactions changed. I previously had something that was in 3 dimensions, and now it's in 2 dimensions. Okay. Thank you. And so much like the pseudo-color plot, which has a lot of attributes, the slice operator has a lot of attributes too. And so I can bring up those attributes and say that I don't want to slice in Y, I want to slice in Z, or I don't want to slice in Z, I want to slice in X, or I don't want to slice in X, Y, or Z, I want to slice by the plane 1, 1, 1, and I want it to be to intersect the location 2, 3, 4, and oops, origin, intercept, aha. It told me that I used the interface wrong, which I did. I want to intercept the location 2, 3, 4. And if I don't want to project it to 2D, then I can turn that button off, and we have it in 3D, and so there's our plane. And if I don't like entering these things by hand, and by the way, I think most of you probably do like entering it by hand because you know exactly which slice plane you want to look at. But if you really want to explore your data, then you can turn on this plane tool right here, and then start manipulating the plane this way and choose your plane location interactively. Make sense? Okay. So I'm going to reset these attributes. And so, in 3D, when I click and move the mouse around, it does rotations. It's a 3-dimensional camera model. In 2D, when I click and move, it's just doing translations because it's a 2-dimensional camera. The rotations and the translations are a product of me being in what's called navigate mode, which is this compass right here. There are other modes, so I can go into zoom mode, and if I go into zoom mode and I click and hold down, it's going to zoom in on that. If I want to undo that, then I would go to view and say undo view. If I really like this one, sorry, I don't have a normal mouse, and I'm using my keypad with 2 fingers, and it almost always goes really well. Here's my Bill Gates moment. Okay, good. If I like it, then I can take a picture of that, and I can go back here and say that I want to reset the view, and I can go over here and take a picture of that and say that I like that one, and then all of a sudden we can go in between camera 1 and camera 2, right? And so you can save views that you like. So navigate, this is our zoom mode. We also have, I'm going to reset the view. We have a line out mode. Oh, thanks, Joe. Appreciate it. Okay, if we have problems, I'm going to switch to this right away. I'm going to try to keep going as I am, but if not, I'll switch to that. We also have a line out mode. And so the idea behind line out is that you can pick a specific line, and then it will make, I may have to go to that mouse. Here we go. And so now it'll make a new plot and a new window. And so this plot is, as a function of distance along that line, what is the scalar field value? And so if we look, now we have two windows. I'm going to put it in the 2x1 layout. If we look at this window, it started in the middle, and then it got a little higher, and then it got low, and then it got really high. And if we look at the curve, it started, I guess, in the middle. It went up higher, it went down low, and then it went up really high. And so VisIt is comfortable with being part of a larger tool chain. And so if I wanted to, I could go here and say File, Set Save Options, and I could save it as an image, but I also could save it as a curve. And so here I'll save it as a curve and say Apply and Save. And then if I go back here and suspend that guy and look at the curve file, here are all the X and Y positions of this line out that I just took. So we're happy to send this information out and let you bring it to Excel or wherever you'd like. Also, the way that I found this line out was by using it with the cursor. If I wanted to do it in a more precise way, then I could go here and say that I didn't really want it to go from minus 8.5 to 2.9. I'd rather it goes from minus 8 to 3, and I'd rather it goes from 6 to minus 9. And then if I clicked Apply, then I'd get the line out corresponding to that line. Okay, so I'm going to go back to this view right here. It should have gone off to the right, but this is one of those things where it's confused about starting in one resolution and then going into another one. So we have our navigate mode, our zoom mode, our line out mode, and then we have these three pick modes. And so I'm going to activate the pick mode, and you can see my cursor's changed, and now it's a plus sign. And so with the cursor change, I can go here and click, and it gives me a report. The report says that I clicked on the file noise.silo, I intersected this mesh, it was at this location. It tells me the intersection is at x equals 3.7, y equals 0, z equals 5.68. That's good because we sliced by y equals 0. If it didn't say y was 0, that'd be really bad, right? It tells me what the zone identifier was, the incident nodes, and then all of the values from those nodes surrounding the location I picked on. Now this report is customizable, and so I could say that I actually don't care about these node IDs. They don't mean anything to me. I'd rather see the physical coordinates. I could say these zone IDs are meaningless to me. I think about things in a logical sense. I want to see IJK values. And then if I were to set those modes and then pick again, now we've gotten something saying that we picked at zone I equals 32, j equals 24, k equals 31. And these were the surrounding nodes, and it gives us the physical locations. And then here are these values for Hardy Global. I could also put in the other interpolation. I could put in the Shepherd Global variable. And and I could also put in, we have a cell-centered variable, Chrome volume fraction. And if I were to put those in and pick one more time, then now it's giving me the same report, and it's telling me about Hardy Global, but also about the Shepherd Global field. And also we have a field that's centered around the cells, not around the nodes. And so it gives me just a single value for that. So this is a report that's customizable. The other pick modes are related. So this was a zone pick. I can also do a node pick, and the idea about the node pick is I would pick and it would find the closest node and then give me a report about that node. And then the last pick mode is a spreadsheet pick, and if you do that, it gives you something that's akin to an Excel spreadsheet with the value at that location and at the surrounding locations, and actually you can do some primitive math operations on that as well. So if I want, I could say this is the region I'm interested in, and then go and say what's the average in that region, and then it will say here's the average of those selected cells. So, so those are our pick modes. Okay, good. Interaction modes: navigate, zoom, picks, line out. Good. Here, now we're back to our, oh, I didn't want that. I was still in the pick mode. I'm going to go back to navigate mode. So now we're back into 3D, right? And so I started by showing just one operator, the slice operator. Let me show a few of the other ones. One of them is the isosurface operator. So with the isosurface operator, here we have 10 isosurfaces of the field Hardy Global, and we're also coloring by Hardy Global. Now, we don't have to take an isosurface and color by the same thing. If we wanted to, we could take an isosurface of the field radial. And so the radial field is 0 here and gets bigger and bigger and bigger. You can see VisIt tries to be smart. You don't have to say what values you want it at. You just say, I want 10 levels, and it picked 10 pretty good levels. Alternatively, we could have said, I know what values I want it to be. I want it to be at 5, 10, 15, and 25. And if I do that, I'd get those 4 values. You know, maybe we can say, I want you to pick levels, but I want you to pick them all between the values of say, 15 and 30. And then we get those levels. And so I guess the point I want to make is, much like the pseudo-color plot, much like the slice operator, every one of these plots and operators has a set of attributes that allow you to carry out, you know, the operation in a way that makes sense to you. Okay, isosurface operator done. We have a 3-slice operator, which can sometimes be useful for exploration. So this is just 3 orthogonal slices. I showed earlier that we have a plane tool that allows you to adaptively set the plane position. We also have a point tool, and so you can move the point around and then look at different cross sections. We have a box operator, and so this restricts the data to a region, and so you can say I want it from x from 0 to 10, y from -5 to 5, and z from 3 to 7, and that restricts it to a box. And so I guess, you know, one of the things that I'm working up towards, and I want to say a little bit of the punchline right now, is what I'm going to show is a lot of interoperable actions that you can perform. And so we're going to build up to being able to make new fields, being able to do analyses, and then these sort of operations where you can do selections are really useful, right? You make a new field, you do a selection like, say, I'm interested in things within this box, and then I want to analyze what's in there. And so I always find when I do the tutorial that this is kind of the slow part of the tutorial, just kind of saying, oh, we can do this, we can do this, we can do this. But you know, it's useful to have a sense of what these operations are that allow you to do selections. Another one that I want to show off is our clip operator. And so here we've clipped by a plane. We could also clip by a sphere. So this should be everything, I think, outside a sphere of radius 12. And we could also say we want everything inside a sphere of radius 12. One more operator I want to show off, and that is our threshold operator. And so with the threshold operator, you can put in as many variables as you want in specified ranges. And so the default variable, the variables we're coloring by, is Hardy Global. And so we can say that we want to see things that have a range between 4 and 5. But, and so then these are the cells that meet that criteria. But we can also say we want to see things where the shepherd global is between 3 and 4. And so actually not a lot of cells dropped out there. If you have, you know, a given cell has 8 different values at its 8 nodes, because these are hexahedrons. And so I'm going to say that I only want to see the cells if they're all within a range. So all of the points are between 4 and 5 for the Hardy global, and all are between 3 and 4 for shepherd global. And in fact, here are some cells. And so for these cells right here, every single point in the cell got interpolated to be being between 3 and 4 for shepherd global. But with the other interpolation scheme, the Hardy global interpolation scheme, every single part of the cell got interpolated between 4 and 5. So this is an area where the difference between the two is pretty high. Now, let me jump ahead to our expression language. So expressions are how we make new derived quantities, so we can take the existing fields and then make new ones. And so if I wanted to, I could make something called diff, and I would say that it was Hardy global minus shepherd global. And so this would let me look at the difference between the two fields. And then I'm going to delete the threshold operator and look at diff. And so here we can see that since this was Hardy global minus shepherd global, well, we can see that this range up here goes from, you guys may not be able to see this, but the max is 1.09 and the min is minus 1.57. So there is actually a pretty big range between them. You know, we can bring in some of our other operators, so we can do isosurfacing, and maybe we want to look at all the places where they're more than 0.5 away. And so in the green regions, it would be, well, isosurfaces are sometimes ambiguous. Let me actually do this. I'm going to make an iso volume operator, add an iso volume operator, which will find regions, and we'll make the upper bound be minus 0.5. So this is the region where Shepherd global is considerably bigger than Hardy global. And similarly, we could have had from 0.5 to the max. This is a region where Hardy global is considerably bigger than Shepherd global, right? So we made one new expression that allowed us to look at the difference between the two. We also could have done more sophisticated things. So rather than doing difference, we have some built-in functions. So we could put in absolute of Hardy global minus Shepherd global. And then if we tell it to recalculate with that expression, these are the regions where the difference is bigger than 0.5 in either direction. Now we have a lot of really cool operators in here. Let me do a quick tour of them. So math functions, so absolute value, ceiling, floor, exponents, logs, min, max, plus, minus, times. Vectors, so normalization, magnitudes, dot products, cross products. Tensors, tensor visualization is really hard. So the way people do tensor visualization is they'll take, or the common way to do tensor visualization is you take a sphere and you deform the sphere by its eigenvectors, and the amount of deformation is its eigenvalues. And I'm just not smart enough to look at that stuff and actually learn something meaningful. So I guess if you really train yourself, you can get a lot out of it. What we tend to do is we have some neat things that we'll take. Let's see, tensors. So calculate the effective strain, the effective stress, principal DV toric strains and stresses. Basically to take these tensors and to turn them into vectors and scalars that we can actually understand. Mesh quality, so if you have an unstructured mesh, ways to calculate shape, shear, skew, stretch, taper, warpage, so there are various definitions to measure mesh quality, and you can make new fields that measure those. I will get into comparisons, but we actually have some neat functionality for being able to take fields from one file and put it onto a mesh in another file, which is a very hard thing to do in a distributed memory parallel setting, and then you can do differencing. Miscellaneous is where the really good things are, so gradients, curl, Laplacian. There's actually a lot of neat things in there. Trigonometry, sine, cosine. The notation can get pretty ugly to write, but you can actually do things like if, then, else, and equal to, greater than, equal to, less than, and so on. So there's a lot in here in terms of being able to make new fields. I want to show one off. So this is, actually I'm not going to show it off yet. What I'm going to do is I'm going to come here to this guy, and I'm going to show how it hooks into our queries. So you can see we have a big blob on the outside and we have other blobs inside, and there's a few blobs in between there that are small. And so I'm now going to show off our queries, which are how you do analysis with VisIt. And so I can go up here and go controls, query, and then I can do the connected components query. And so this was one that I talked about in my PowerPoint slides. I can turn on that query, and it actually can tell me that there are 14 connected components in this data set. Let me make one that's a little bit easier to see. I'm going to go back to Hardy Global, and I'm going to do an ISO volume between 4 and 5. So now it's easier to see our components, so we can kind of count them by eye. 1, 2, 3, 4, 5, 6, 7, 8, 9. That might be 10, or they might be connected. 11, 12, 13, 14, 15, 16. And I can go here to VisIt and say, how many connected components are there? It thinks there's only 15. So probably I counted something separate that was actually connected. And you can also get statistics about it. And so if I go and change the display to be just the connected components related queries, I can ask for the volume of each. And so it'll tell me there are 15 components and what the volume of each component is. If I wanted to, I could isolate these components and start doing separate analysis on each component. Getting back to some of the more traditional queries, we have mins and maxes. So I can ask the question, what is the maximum value? it'll tell me the minimum value is 1.09, the maximum value is 5.88. But that's from what's the original data, what's in the file. If I want to restrict it to what's actually being plotted, then I can change the query to be the actual data, and it tells me the min is 4 and the max is 5, which is good because I've restricted the data we're looking at to be between 4 and 5. Yes, sir? Absolutely. Absolutely. So yeah, so good. I may not be able to do it in 20 seconds, but let me give it a try. No, I want to show it off if I can, because the Python scripting is really neat. So let me see if I can do it. So I'm going to go to Controls, and I'm going to say Launch the command line interface. So here's the command line interface, and so I want to say Query Max, and it gives me the max is 5.88. But if I say Query Max, and then I think I just say Actual, then it tells me the max is 5, right? Now, what's really neat, and so what's awesome about the command line interface is you can automate really neat things. And so if you want to make movies, you can get them all put through Python scripts and interpolate your camera positions, interpolate effects within the attributes of these operations. Let me do one really quick. If I go to, I'm going to do an isosurface, and I'm just going to have a single value, and the value is going to be 2. Then, let's see, I'm brave enough to try it. I'm going to say iso equals isosurface attributes. And so these are the attributes for this isosurface operator. And so it looks like if I say, but you see, these are the default attributes. What I really want are the attributes of what's currently being plotted. And if you put that 1 in there, that's what you get. And it says the contour value is 2. And if I were to do iso contour value equals 2.5 and set operator options with iso, then we got a different isosurface. And so where it gets really neat is you can say for I in range of 50, iso.contour value equals 2 plus 0.1 times I. Actually, let me do 0.05 times I. And then set operator options with iso. And if I wanted to make a movie, I'd just say save window right there, right? And it would just save an image for every one of these. And if I press enter, you can see it's actually animating the isosurface here, right? So that is not very much code to be able to do some sort of interpolation. And similarly, if we want to do, move a cross section through, that's an example that we normally do in the longer tutorial. That you have a cross section, and then we integrate how much mass is there at the cross section, and then we animate the cross section through the volume. And as we do it, we construct a function which is as a function of x position, how much mass is there at that x position. And it's about 10 lines of Python code. So here, I guess, let's see, I'll try to reproduce it really quick. If I make a slice, let me show something else off real quick. So I haven't really shown any of our other plots. We have lots of ways to render the data. I didn't show volume rendering. I haven't shown streamlines. I will show really quick our filled boundary plot. And so our filled boundary plot is the way that you look at material boundaries. And so in this case, everything on the exterior of this is air. I can go into our subset window. And so a lot of our data sets have different subsets. Now we've got a cross section of Chrome VF. And so we could go to our controls query and say, what is the, we should call it integration. We don't. We call it weighted variable sum. And the reason we call it weighted variable sum is we want to distinguish from the times that you don't want to do weighting. If you have density, as you integrate, you want to multiply by the volume of the cell. If you have mass, you've already pre-multiplied by the volume of the cell. So you just want to sum those masses up. And so we distinguish between variable sums and weighted variable sums. So if we did a weighted variable sum, it would tell us that the total Chrome volume fraction on that cross section is 32.74. And so if we were to go back to our Python interpreter, I'm not quite brave enough to just type this one in because I'm sure I'm going to make a small problem here or there. Let me just try typing in as some file called t.py, or since it looks like I've done something like this before, t2.py. And I'm going to say for I in range 50, s equals slice attributes, and I'll want to change the intercept, the origin intercept, to go from minus 10 to 10. And then I could say query weighted variable sum, and I could make an array, and then I could say t equals t plus get query output value. So we'll live on the edge and just source that and see what goes wrong. Thank you. You guys should be here for all my coding. Okay. I didn't do it right because it's giving me the same value each time out. I guess now I've seen what can go wrong. We get held hostage as it goes through 50 of these. What did I do wrong? Okay. I had the wrong plot active, so it was taking the integral over the previous plot that wasn't being used. So I think if I do this, we actually see the cross-section changing, and we see a different integral coming out each time. And then we've put it into this T array, and so this is now the total sum as a function of the X position, right? And I guess what's I think really neat about this is quite a small script. So, I should comment, if you want to learn more about the VisIt scripting language, if you go to Controls Command, you can actually put in, sorry about that, you can put in Python scripts that you use regularly and actually turn them into macros to make new buttons out of VisIt. But also, if you want to learn how to use the command line interface, you just press the record button. And then if I were to go and delete that plot and then say stop, then it tells me what the equivalent command is. So it actually records all of your commands and gives you the equivalent scripts. So the last thing I'm supposed to do is I'm supposed to connect to 2key. So let's try that right now. And so, earlier when I opened a file, I was opening files on my local host. And so now I'm going to open something from the Argonne 2key machine. So my wireless is working. There it is. And so I'm going to put in my password. Congratulate myself on not saying it aloud. And I put a file out there. Oh, where'd the file go? Here it is, called multi-UCD3D.silo. And when I open it, it asks if I want to launch a serial engine or parallel engine. Also that I want to open a parallel engine with 8 processors and 1 node. And so you can see it tell me this is the command that it ran. That's interesting. So my project has changed. It's become, how do you guys say this? @pesc? When you guys say, this is so great, I'm happy I came to ATPESC? I feel I've contributed to the conversation here. @pesc. So hopefully we're going to get nodes. I tested this several times this morning, and every time I got nodes right away. The queue is hung right now? Okay. Okay. So, what you would see is basically nothing. This prompt would go away, and then all of a sudden I would have connected to Argonne, and I could make plots just as I had before. And the big finale, which I think we won't be able to do, is that one of these expressions, a way to make new derived quantities, we can actually say color by the VisIt's MPI task that processed this piece of the data. And then you see some are blue because they got processed in MPI task 0, and some are red because they got processed on MPI task 7. But otherwise, there's really no difference to the users in terms of whether they're running all on the local host or connecting to a remote parallel machine. So that's it. Are there any questions? Okay, good. So I'm going to be at the coding session tonight. I'd love to sit with anybody who's interested. We can write file format readers. Just talk about how to use the tool. And thanks very much for your time. I really appreciate it.